excited to introduce Rafael Nuñez, who is coming to us from UCSD. And he'll be talking about whether or not there is a biologically evolved capacity for number. So thank you very much. Please join me in welcoming our speaker.
Thank you very much. Is this working? Who's in charge of this? It's working. Good.
Yeah,
Thank you.
It doesn't go through the speakers. It just goes to the
Yeah, sounds good. Well, it's a pleasure to be here. I was looking at the archives and looked like I had a couple of talks I was just commenting to Dan. Like 2006 was one talk I gave here in this room, and 2012 maybe another one. I remember Chuck Goodwin sitting around there and having a heated conversation those years. Anyway, memories. So, pleasure to be here. What I want to discuss today is this very question. The question of, is it really there's a biological capacity for number? And when we look at these kinds of things that humans do, like windsurfing or piano playing or tool making, in vitro fertilization and so on, snowboarding, domestication of animals, etc. These are all kinds of behaviors and capacities and things and abilities we develop that actually are built on huge amount of cultural scaffolding, but at the same time building on biological evolved preconditions for those cultural activities to be developed. So the question I want to ask today actually has to do with the issues of number and arithmetic. So it's easy to see, for example, that piano playing or writing music is going to need at least, for example, cultural conventions for writing, which you won't find, let's say, in the origin of Homo sapiens as a species 200 and something years ago. Same thing with windsurfing. Not only you need balancing, the vestibular system being recruited for, some kind of balance and equilibrium, but you also need a lot of cultural development for materials and learn how to do it in kind of know-hows, which are very sophisticated. And you can sort of see the same thing for things like domestication and starting to have different kind of nutrition, because all of a sudden offspring can start drinking milk from another species and so on. So the question I want to talk about is quantification, an exact quantification, as we'll see in a minute. And what is it about number and arithmetic? Can we find sort of arguments for saying that there's something specific about biological endowment when it comes to number and arithmetic? Or is it a pure cultural development, as some other people have argued? What I want to start with is essentially certain things that have been studied since the 1940s. One of them is this capacity we all seem to have to discriminate in a very fast, efficient, error-free way amounts of, for example, dots, quantities of dots. We have immediate response is error-free. We don't need language or culture to really come up with this capacity. And you observe that in many other species, non-human animals, able to discriminate that. But when you increase the number of dots, then this capacity is not so clear, and then actually is limited to a certain amount or quantity of dots. And this was studied in the 40s. It was named Subitizing as this sort of particular type of response in these cases. Now, this has been studied way more now in cognitive neuroscience, in developmental psychology, and animal psychology, and so on. Very robust piece of info. Now, there's another mechanism also that is being understood, is this sort of capacity to discriminate amounts, let's say, of which one has more black dots. And when they're in certain ratios, for example, it's relatively easy to see that some of these would have more black dots on the top and maybe more white dots on the bottom without knowing exactly how many. But the capacity to distinguish and discriminate shows up. Now, when the ratio starts to be close to 1, for example here, I don't know, how many people think here you have more black dots? How many white dots? Some people say white. How about here? White. Hard to tell. But if I say how many people think here is white more than black, everyone agrees that then it's more. So this has been dubbed as a large quantity discrimination. Now the convention wisdom tells us now, when you look at the literature in many areas, in cognitive neuroscience, in developmental psychology and animal cognition, that these are arithmetic or mathematical abilities you find already in monkeys, and you find it in kids before they are language driven, let's say, beings. And you find that in arguments in, that there's actually arithmetic done at the level of single neuron level, and then you see, journals publishing numerical arithmetic abilities in non-primate species, numerical cognitions in bees and other insects, and on and on and on. Then the media takes over, and you have articles like, this is in the New York Times, many animals can count, some better than you, going over, details of these sort of capacities that human and non-human animals seem to show with the discrimination of these quantities that I was just mentioning. And then it goes on and on and on, looking at other species giving clues of the origin of number. National Geographic telling you that fish as good as college students in number tests, and asking the question, are you as smart as a mosquito fish, and so on. So of course when we want to do science, it's like, okay, this sounds like maybe can't be true, but so what is the science behind this? And the conventional wisdom essentially says there's a biologically evolved capacity specific for number and arithmetic. And specific here is very important. So we're not talking just about domain generality, we're talking about domain specificity, about number and arithmetic. So what I want to ask here is the question, well, is this really the case? And there was an issue we had like a year and a half ago or something, in which we asked precisely this question. And when I was starting to do like a review of the literature in cognitive neuroscience, in animal psychology, in developmental psychology, and so on, and also linguistic anthropology, you could see that there's a huge confusion, terminological confusion, in what counts as number, what counts as counting, what counts as numeral, numerousness, quantity, numerosity, and so on. And that also leads to confusion in what counts as arithmetic, what counts as mathematics, and so on. So if we want to do science, one basic thing we need is to clear the table, clarify terminology, and not just because of the sake of being picky, but for the sake of avoiding confusion in theoretical developments and hypotheses, concoction of hypotheses, and so on. So when looking at that, I just want to go over the following today. So first I want to show the kinds of problems that have been identified in terminological in these areas. And this has led to very like a bad practice, I would say. It disappeared really. Maybe the psychophysicists of the 50s were really picky about certain things, and unfortunately that terminology got dropped. But bad terminology with teleology is really a bad combination. So that's what we're going to argue at the beginning. I want to go over certain issues of data, overinterpretation of trained animal data, overlooking crucial human data, and then some distinctions that I'm proposing that I think are relevant for these kinds of questions, and at the end I want to finish with hypotheses that for the moment I'm calling like the biological enculturation that you need in order to understand these kinds of things. So let me start with the first one. So loose terminology, the first problem we find is that number is a highly polysemous term. So not only you have different meanings in everyday language, like when you say, what's your passport number, what's your phone number, there's a number of things and so on. The term number there, the lexical item, has very different meanings. Even the passport number in some countries could have letters in it, and actually it doesn't have arithmetic properties, it's just numerals and so on. In fact, a phone number could even be chromatic, Could just be like, green, red, blue, white. And that's my chromatic, phone, let's say. So we don't really need the quantity in it and so on. Even in mathematics, ordinal numbers, infinitesimal numbers, transfinite numbers to real numbers, they're all different kinds of numbers with different types of properties. So number in itself is already a problematic term because it's highly polysemous. So in the literature now, you find a lot of confusion between a numeral, which is the sign for a number, not the number itself, and the concept of number, or quantity and numeral. And sometimes people do research on numerosity, but they claim that the conclusions are about number, and so on. So numerosity is an interesting concept because numerosity was coined by the psychophysicists in the 50s to measure the numerousness of a stimulus. In the same way you measure thermic properties with the Celsius or Fahrenheit scale, numerousness, which would be the equivalent to thermic properties, would be measured by numerosity, the scale that the experimenter has. And this is not the same as number, and so on. So, and then you have today's uses of number when it's exact, when it's approximate, when it's symbolic, when it's non-symbolic, and so on and so forth. So it's a big mess, which was already detected by people in the 80s. So the question then is, when we talk about numerical cognition, numerical abilities, numerical processing, numerical tasks, numerical stimulus, and on and on and on, what do we mean by numerical, when in fact you have all these various things being messed up? So we need to figure out what is this term standing for when the claims, when the hypotheses are built and conceived. We need to know what is this entailed. And the literature is pretty messy in that sense. Now the problem is when you take certain things like, let's say numerousness discrimination in a teleological form. So now you think that numerousness or number is a natural kind, like many cognitive neuroscientists think, or that is the primitive to explain the phenomenon, or it is a pre-existing entity that pre-exists humans. The numbers are just there, out there in nature, therefore we need to find out how is it that we connect to them and so on. Or when it's conceived as like in the case of the approximate number system, the ANS, which is pretty in the standard theory these days, then it's part of the explanandum. So we want to explain number, but in the explanation of number, we already have number in it. So it creates these circularities that are theoretically complicated. And when they are taken in a more nativist form, they go into this sort of teleological argument that numbers are already somehow in the brain in the form, an innate form, in the sense like this approximate number system I will describing. So that's the kind of thing that you see arguments for evolutionary foundations, for example, for ANS, where now number is in it, is built into what is evolutionary biologically endowed. Okay, so big complications, and to be honest, in a book I wrote with 20 years ago now, with George Lakoff, we also made the same mistake. In chapter number 1, we call the brain's innate arithmetic, and we talk about number discrimination by babies. Today, I think this is completely wrong. This is not the arguments in it, but the misnaming these capacities because they just create confusion. Babies don't discriminate numbers, I think. They discriminate quantities, and that is a very fundamental thing. So I think these are theoretically misleading misnomers. We now should be much more careful, not just the two of us, but I think the entire community interested in understanding these kinds of things. All right. So another problem is the field has a lot of overinterpretation of trained animal data. For example, results from training are often very hard and require considerable environmental support. So if we want to understand the evolution, let's say, this is not a setting in which we can get deep insights into what kinds of quantity-related abilities are involved, because you have a whole setup in which the non-human animal in this case trained, is interacting with devices and stimuli that are conceived for specific purposes by humans. So without going too far, you could say you could train other non-human primates to do certain kinds of things, and they can do it after training. The question is, we may gain insight to many things, but do we really gain, in this case, for example, good insight into the evolution of the locomotion of these particular species? That's the kind of question I want to raise. So we can put animals in human settings for certain kinds of purposes. The question is, how far can we go in order to interpret the results in terms of evolutionary arguments? Indeed, research shows, for example, that training a monkey on a simple quantity matched to sample task can take over 4 months and 20,000 trials only to achieve discrimination of collections at a 3-to-4 ratio, and with it only 75% accuracy. So we may train these abilities that we showed at the beginning to improve a tiny bit, but whatever we're doing there has a very low ceiling, and it seems to be quite different from the kind of notion of number that we have these days. That 7 is distinct from 8, categorically distinct, not likely to be distinct, or is 75% of the time different from it, and so on, which have more perceptual basis. So the other thing is that unsuccessful training usually doesn't get reported. So you only get the big stars and doing good things, but you rarely see, and this goes back to the work by Hank Davis in the 90s, who already pointed out to all the problems of mixing terminology in this particular field. And he said in that BBS, very famous BBS paper, then these are all these abilities, right? They're no mean feat. And for each of the successes you have heard about, they're untold failures. Although the non-dissemination of negative evidence is the way science normally progresses, you normally don't publish negative finding, it is particularly unfortunate in the case of numerical competence in animals because it clouds the question of how general or easily established this ability truly is. And this is part of the problem too. You get to publish something when a pigeon or some rat or some does something with a certain level of performance, and that gets published, and then the media takes over, and then it goes on like a snowball. But in fact, the number of cases when it does not work is tremendous. And I've been fortunate enough to visit some sites when one of them with Tetsuro Matsuzawa. Interesting, they have very amazing results with Ai and Ayumu, the son, but I was able also to see all the males who couldn't do anything because the level of frustrations was so high, they were just hitting the computer and just screaming all the way. They couldn't learn anything because frustration was so high, so they're never in the mood for learning, and so on and so forth. So yeah, you can see that this Ai, or Ayumu, the star chimps, can do all kinds of things under certain conditions if they have a good tolerance for frustration and all kinds of things. But the claims that we can make then that chimpanzees, evolutionary speaking, can do A, B, and C, then should be more seen with taken with a grain of salt. So, in fact, the other problem is that often a criteria for success is very low. Usually, anything above chance is taken as a success. So if you are able to discriminate a certain ratio of quantities above, let's say, 60%, and it's like, oh, okay. If fish can discriminate certain kinds, oh, okay, they already have the ability, and so on. As I was saying, some of these 20,000 trials, you get 75%, that counts as okay, and so on. And the other problem is that there's lack of validity regarding exactness, which is one of the properties of exact quantification, in the case of number, and these categorical distinctions that are needed. So the fact that for the number 8 is distinct from 9 categorically, not in terms of perceptual noise. All right. So the trained animal, oops, I missed my little conclusion there. The trained animal data then inform many interesting questions. No doubt about that. It's not a criticism of that kind of thing. However, in order to have evolutionary arguments of how these capacities have been biologically endowed or to what degree and so on, then we have to be much, much more cautious than what we have been in, when we look at the literature. So let me get now to the next point, which is, yes, there's a lot of attention to non-human animals to see what animals can do and how amazing behaviors they can perform under certain training conditions and so on. But if we really want to look at evolutionary arguments, we should stay also within the same species and look at human data that has not been taken, I would say, seriously in this debate. In fact, to begin with, there's a huge bias because most of what is called numerical cognition has been done in industrialized societies. A lot of the participants in these studies are college students because it's very cheap and easy to get them. You just give them a little bit of credit and then you make the big theories of how the human brain processes numerical things and so on. So we have this sort of biased way in which we look at humanity by just looking at certain type of humans which are trained and told how to do things for early ages. And this, of course, has problems for making claims about evolution again. Writing, for example, is extremely recent. It's only appeared 6,000 years ago. The species is, let's say, 200 and something, depending on who you ask. So we have 194,000 at least years without writing. But not only that, this only occurred in a few places. So not just in Mesopotamia. You have in China a little bit later, in Mesoamerica with the Mayans. But most of humanity never did any writing whatsoever. There are estimates I hear, for example, in Europe in the Middle Ages, the amount of people who know how to read and write was less than 5% in Europe in the Middle Ages. So when we say this is the area of the brain that deals with reading, this is the area of the brain that does arithmetic and so on, we're already looking at biased brains that have been shaped in the ontogenes of individuals, in the lifespan of individuals. So making claims about evolution in the terms of natural selection then is pretty hard. So writing really is an accident, late accident, and not to mention then the arithmetic you do through writing and the number symbols that you have, numerals. So that's one problem. The question then is how about quantity in non-industrialized societies? Maybe they don't have writing, but how do they deal with quantity? And when you look at that type of data, one thing is interesting is that all languages that have been studied so far, they all have in one way or another natural quantifiers. Few, several, many, and so on. But by no means they all exhibit exact quantification. And this is very important to distinguish. So quantifiers, natural quantifiers, yes. But you don't do arithmetic with those. So many times many doesn't give you a regular arithmetic. So language, many of these languages are incredibly sophisticated in the deictic systems, in temporal tenses, and all kinds of sophistications, but not with exact quantification. And the most striking example is Aboriginal Australia. So Aboriginal Australia, a recent study, a recent survey of about 200 languages from 13 different linguistic families found that nearly 90% of these languages, which cover the entire island, lack numerals beyond 5. So these would be examples of those like 1, 2, 3, so-called 1, 2, 3 many languages. But it's not just anecdotal. It's not just one crazy language in the Amazon or one weird language in... This is almost the entire island of Australia. And now, evolutionary speaking is interesting because Australia now, we know from a recent Nature paper a couple of years ago, started to be inhabited by humans 45,000 years ago. 45,000. Just to give you a reference here, for example, the Proto-Indo-European language, which is supposed to be the origin for languages as diverse as Farsi and Hindi and European languages like Swedish and Icelandic and Portuguese, they all have a common ancestor, the Proto-Indo-European, 7,000 years ago. So here we're talking about 45,000 years. And these are humans who have been living in the island, raising kids, moving around, migrating, hunting, gathering, and so on, apparently with very sophisticated languages without the need of exact quantification. So this is the kind of data we need to take very seriously. And other work by BEPs and colleagues showing that, for example, in hunter-gatherer languages, about 200 in different areas in South America and Australia and so on, they also, maybe not to this extent, but today exhibiting pretty much the same. So numerals or signs for numbers in the subitizing range, but not above. But at the same time, showing natural quantifiers in ranges that are higher. So there's no distinction between 9 and 11. That is not needed, hasn't been needed, there's no term for it, but you have natural quantifiers. So the point is that all languages, and cultures that study so far, do have natural quantifiers. So that's an important piece of datum. But exact quantification is far from being universal. And this has been also studied and analyzed by Caleb Everett in an interesting book that I recommend, because he also did study it in the Amazon and some of these languages. What's the moral of this section of the talk? Is that language by itself does not lead to number. So some people have argued that the difference between humans and non-human is language, and therefore we have numbers. Well, that's not true. If we look at the data of the Amazon, many hunter-gatherer societies, and especially Aboriginal Australia, those have languages. There's not a single society without language. And they're very sophisticated in many aspects of the linguistic diversity. It's just that they don't have exact quantification. So it seems then that language is maybe a necessary condition, but is not sufficient for exact quantification. And this then is perhaps a cultural trait, not a biological trait. So moving now to the next point, it looks like we need to clarify what counts as I said at the beginning, counting, numerousness discrimination, numerosity evaluation, number, and so on. So let's dig a little bit into this. So if we have a visual apparatus, a perceptual system that could discriminate, let's say, chromatic aspects like red and green, or numerousness, amount of, but perceptual, psychophysical, let's say, driven, that may be trained, but in fact, it works very well in the subitizing range. You don't need training or language or culture. You just have a psychophysics of it that would lead you to discriminate with error-free and very fast. But by the time we call this 9 dots or 8, and we uttered a sound, vocalize a sound like 9 in English, or write it with another conventionalized system, write the sound in words, or with a digit, and so on. As soon as we do that, we are in a completely different realm, because that involves symbolic reference. And now I invoke this because I know Terry Deacon was here not long ago, probably talking about symbolic reference, and I'm going to build a little bit of on that work to continue this part of the talk. And symbolic reference is now different from perceptual activity to discriminate quantities that you may train a little bit, but it still remains in that perceptual domain. Numerals may change, may vary tremendously. You can say nueve in Spanish is a different sound. You write it differently. You could use other types of forms for non-strictly positional notation, like Roman numerals, denoting the same quantity, the same concept. Or you can use another base. Let's say you can write 9 in base 3, which would be this. Or you could write it with infinite decimals, like 9 would be written this way. All these are standing for 9. And if I had, let's say, 5, it doesn't matter how I write this, but I could say things like 5 is a prime number, the concept of 5, which is independent of the numerals I use to refer to number 5. Same thing with 8, etc., etc. So all these are numerals that we have created that have different rules and different properties to refer to some other thing, but its symbolic reference is crucial here in this process. And the other important thing is that this conceptual apparatus now that we are referring to through symbolic reference is also relational and operable. So the number 17 is not standing in thin air. It stands with relative to other terms that are in the same family, and that is very peculiar to these kinds of conceptual system. If you look at your dictionary in your computer, you would see that, for example, 8 says is a cardinal number. This is just the dictionary in my laptop. And it says is equivalent to the product of 2 and 4, 1 more than 7, or 2 less than 10, and so on. These are all relational properties trying to tell you what 8 is. There's not just 8 is that sound that we say by saying this sound. It tells you the, products, operations, subtractions, factors, and so on. So number has all this richness, which is way more than just these perceptual basic abilities. So then, what is number? Well, as I said, it's a highly polysemous term and so on, but we could be a little bit pragmatic and maybe focus on a prototypical properties of what number is. So let me do a little thing here. Let me say I'm going to buy you a beer if you guess the number I'm thinking of, which is between 1 and 5.
4, 3, 1.
Sorry, it was square root of 2. So, yes. That means the prototypical idea of a number is not an irrational number, is not a root, is not a logarithm. It's just 2, 3, 1, because those are the counting numbers. It's just a little example of prototypicality that you have in many categories. Birds and, mammals. So a dog may be more prototypical than a whale, even though they're both mammals. But in human cognition, dogness is much more a mammal, let's say, than a whale, and so on. Numbers is the same thing. So why don't we define, just in this pragmatical sense, what are these counting numbers? And I want to make a distinction between the prototypical counting numbers that we use 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, and so on, from natural numbers. Because natural numbers is a late development in the history of mathematics. It has all kinds of issues with axiomatic systems and so on. And within natural numbers theory, a number like, that you could write with the following digit, 2, 3, 9, 8, 5, 6, 8, 8, 8, 8, 9, 0, 1, 5, 1, is as natural as 3, because they both are members of the same set. Well, in the mind of cognition, those are not the same status. Much more prototypical is 3 than the one I just said. So if we want to define prototypical cases, these are 7, maybe not fully exhaustive, but properties that we should consider. First is that it quantifies exactly. So unlike many or few or several, or even the use of a couple and things like that, it quantifies exactly. Second, it is abstract in the sense that it transcends psychophysical perception modality. So you may count sounds, beeps, flashes of light, and then quantify exactly those stimuli. It would have a cardinal sense because it's associated with a collection of numerousness in an exact way, and it has an ordinal sense by the time you count them. It has a progress in time to determine the cardinality. It is relational, as just said, so these concepts don't stand separate in thin air, and they are operable and combinative. So you create new numbers based on previous numbers. You can look at, let's say, the linguistic anthropology side of it. Usually you have monomorphemic cases for the subitizing range, and then you have compositions of those, like 2 4s, or 8 10s, and things like that, which shows in English, it shows in morphemes like the teens, or the ty, like 40, 50, and so on. So combinations of simple blocks. And crucially, as I said, number is referred to symbolically. And that is going to turn out to be a crucial property in this case. So number, in the case of prototypical counting numbers, what it is really is a quantifier. A number is a quantifier, but it's an exact symbolic quantifier. So that seems to be quite different from, let's say, what monkeys or other non-human animals are doing training by trying to do with via associative learning, discriminations and getting the responses up to a certain degree, but they don't quantify exactly. They may be abstract sometimes when you transcend stimuli modality, but certainly not necessarily refer to symbolically capturing the properties of exactness and so on and so forth. All right. So if we want to do good science in order to ask these questions, we need to have clear, non-confusing concepts. So how then to properly refer to biologically endowed quantity-related phenomena like subitizing and large quantity discrimination when these don't satisfy the prototypical number properties? They're not exact and so on. So how can we have different terms for whatever is going on here and what's going on as soon as you start recruiting symbolic reference capacities? So essentially, we seem to have built-in biologically endowed mechanisms for discriminating chromatic properties, numerousness properties, quantity properties. But how are we going to call them if they're not numerical in the sense that they lack these properties I just referred to? Numerical is confusing because if I say that these are numerical, I'm bringing in all this baggage of being, having almost proto-arithmetical properties and so on, when in fact they don't. So not a good candidate, and it's confusing. How about quantitative? Well, quantitative is super loaded because it's opposed usually to qualitative, as if this is something that belongs to a different realm, the cognition, so brings all kinds of baggage here. So because the English language doesn't have an adjective to refer to these capacities that are biologically endowed, but that do not have the number properties that I just referred to, we need, I think, in order to do the science of this, I'm assuming we need a different adjective, which for the moment I'm calling it quantical, to say is not numerical, but has to do with quantity, and there is quantical cognition, quantical perception, quantical stimuli, quantical that would be different from numerical, and we don't have to ascribe numerical properties until we observe those in the experiments that we do. So in this article I was trying to say, well, how would that show up? Well, let's say if we have some kind of representation here on its kind of a disk of how we handle discrete quantity, and kind of for logarithmic compression I have, like, say 1, 2, 3, 5, 10, 1,000 and so on. If we have going from something purely non-symbolic like subitizing and large quantity discrimination, the two examples I showed at the beginning, all this is pre-symbolic. There's no culture or language involved. Non-human animals have it from as soon as they have some kind of perceptual system going on, biologically endowed. But as soon as you have, on this side of the symbolic reference gap, as soon as you have natural quantifiers, even if they're not exact, like a pair or a trio or few or many and so on, you are in the oral language convention side of things. You may have body signs, you may have material artifacts that may lead to exact quantification. Then, of course, written numerals and non-positional like Romans, strictly positional like what we use every day, but then more and more complicated type of notations for complex numbers, etc., etc. The point is, we have this gap, and this gap seems to show that whatever we have here looks like it's biologically endowed. Many animals would exhibit these properties with no non-necessity for having linguistic, cultural scaffolding. And whatever is on this side of the gap is not biologically evolvable. And here I want to take Terry Deacon's quote again. It says, symbolic reference must be acquired by learning. And this happens in the ontogeny of individuals. Lacks both the natural associations and transgenerational reproductive consequences that would make such references biologically evolvable. So in the same way that you don't have something like you evolve genetically, let's say a language that would have a certain deichic system like in English and it would have this, that, these, those, then those specificities are part of this realm. Not biologically evolvable, you need a particular type of symbolic reference that has to be scaffolded by other individuals, namely culture. So that brings me to the last point. Enculturation and the biological apparatus that supports enculturation. And this beyond pure natural selection. So in that paper, which is the one I was referring to, one of the things that I was raising was the issues of teleology and terminology and so on, but was the issue that is not just biological, but is not just cultural. NIDA, who is a famous, well-known primatologist and neuroscientist, when responding to the debate, he titled, and the arguments are based on, essentially summarized by the title, it says number faculties rooted in our biological heritage. And of course, no one would disagree with that, and I would not disagree with it. It's, of course, it's rooted. The problem is that rooted is a very open term. What does it mean, rooted? Anything we do is rooted. Writing is rooted. We have hold the pen with a certain type of anatomy, morphophysiology that holds the pen. Windsurfing, watching movies, all those are rooted in biological heritage. So what does it exactly mean? In the response to that argument, I kind of more developed that idea that you need enculturation, but you need a biological apparatus that would support that enculturation. And that doesn't exist in all species. Not all species support symbolic reference, for example. And if you don't have that, then you can't launch a system like arithmetic, for example. So this is what I want to put a little bit emphasis today, is the enculturation part of it, how a society and a culture scaffolds new individuals in this conventionalized system, but recruiting biological apparatus that would support that. So it's not a purely social, cultural aspect. So exact symbolic quantification, beyond subitizing range that is, so beyond 4, 5, 6, and so on, appears to be motivated by cultural preoccupations. Like tracking variables, so you need to have a society that has variables. And you need to care about the distinction of this many and this many to the point that you label the difference. Stock management, trading, accounting, and so on. And that seems to have appeared with the Neolithic settlements. The first time in the history of humanity when you're not hunter-gathering all day and scavenging and eating what you collect as you move around, but all of a sudden you settle somewhere and then you start to have the first cities. And as soon as you have that, you start to stock food and goods, and someone at some point will start to make the accounting for keeping track of those goods and so on. Now, that occurred 10,000 years ago, and it took about 4,000 to develop something like writing. But all that is now quite documented these days. So it has to be supported, and hence by tools and materials that are, again, culturally developed and that facilitate offloading cognition. So human cognition is incredibly poor in terms of working memory. We can only hold a certain amount of information at a time, at any given time. So we need to, and that's what writing is all about, we need to mark, we need to put aside certain kind of offload part of that to continue the process and so on. So material anchors are precisely that type of physical devices that are culturally created. And all this requires enculturation. You don't invent these things from zero as an individual. You come in a society that starts to using these kinds of things, and that's when enculturation comes in. Writing technology, as I was mentioning, would be one of them. So if you're a young Babylonian kid hanging around people who do the accounting, because by no means all Babylonians knew how to read and write, only a few, So, but if you're a kid hanging around there, then you start to learn that kind of system through, again, enculturation. You may have other cases without writing, but that would support quantification. For example, the quipus from the Incas in the highlands of South America, they did not have writing. They built the most amazing building with astonishing precision, like the stones put in Machu Picchu, for example, but without writing, apparently. However, they had very sophisticated forms of keeping track quantity-related exact quantification and quantity-related patterns, calculations, color-coded and also coded via very sophisticated patterns of knots and distances of magnitudes and things and so on. So this is, again, offloading cognition, and you need to learn how to use them. Other Polynesian languages have very sophisticated grammatical or lexical tools, even though they're not written, but they can keep track to a certain level of basic, quote, arithmetic when you have lexical items and relational markers that you could track through language and so on. The point is that you need conventionalized symbolic reference for exact quantification, and this seems to be, again, outside of natural selection proper. So when there is number, it's not always the case that you have number beyond subitizing range, but when there is, it's interesting that commonly is with base 5 or 10. And you would say, well, why is that? Oh, because we have 5 fingers. Sure, that's pentadactylism. It evolved in many species. You know, gorillas, chimpanzees, raccoons, they all have pentadactylism, but they don't have numbers in the way. So they could have evolved anatomy and patterns of morphology, like pentadactylism, but they have not apparently evolved symbolic reference. So the fact that we have 5 fingers, yes, we have 5 fingers, but to recruit those to symbolically stand for a number is an entire different thing. And in fact, it shows by the variations that we have in interculturally, cross-culturally, of how, let's say, you denote the number 8. It's not because you have 8 fingers. Different combinations of what you count. Do you count the, each individual finger? Do you count this part of the anatomy where you flex the finger? What is that you count varies and is, again, scaffolded culturally. So that just because we have the anatomy of pentadactyl properties, that doesn't mean that symbolically could stand for a number. And then when there is written, interesting research shows that, for example, even for the most basic tasks, like comparing digits, whether some digit standing for number is odd or even, or very simple. Some research, for example, by Tang et al. Showed that, for example, if you do compare Chinese native speakers and English native speakers for very simple tasks like this, you would have different brain activation just for those numerical tasks based on numerals, Arabic numerals, the same stimuli for both, but you would see, for example, more activity in the premotor areas in Chinese people that you would see in the English speakers, and the English speaker you would see much more, let's say, in the classic sort of linguistic areas, like Broca's area or Wernicke's area, which you would not necessarily find prominently in the Chinese. These are the same Arabic stimuli, the Arabic numeral stimuli, same question, but apparently recruiting different types of neural populations for making sense of the question and come up with an answer. So this seems to be mediated now by culturally shaped cortical, sort of phenotypical plasticity that would support the type of enculturation that drives to exact quantification. So number then is language mediated, is conventionalized, and is exact symbolic quantification. And that's what it is, and apparently it's a cultural trait, not a biological trait. And this has maybe occurred only recently. It's ubiquitous nowadays in our society, so we take it as if almost as if it's always part of nature. But it's been apparently largely outside of biological evolution, and if we live in the Aboriginal Australian data, for hundreds of thousands of years, 190-something years, with no necessity for exact quantification. So it's probably certain that it builds on biologically evolved preconditions, like subitizing or large quantity discrimination, these psychophysical capacities, but is motivated by preoccupations and practices that are culture in nature. And this is now the point, supported by other things like material anchors, like the quipu and the Incas, or conceptual tools and so on. But you need the biological apparatus, this certain type of neural populations, to be recruited for something that did not evolve for, but they're recruited given the ontogenetic development of individuals in a particular society that cares about those distinctions. So I want to kind of start closing with a quote by Theodosius Dobzhansky, famous geneticist and evolutionary biologist, who said, human evolution has two components, the biological or organic and the cultural or superorganic. And usually these are seen as separate. And actually in many departments of anthropology is kind of vividly seen, unfortunately. But these components are neither mutually exclusive nor independent, but interrelated and interdependent. Human evolution cannot, and this is human evolution, not just any type of primate evolution, human evolution cannot be understood as a purely biological process, nor can it be adequately described as a history of culture. It's the interaction of biology and culture. And that's, I think, precisely the spirit of this sort of approach that unfortunately is not seen much in cognitive neuroscience, developmental psychology, and animal cognition these days. So the question really is not whether number is a purely cultural development, as many people who are not in the nativist camp would start kind of think about. The question really is this capacity, number, let's say, a domain-specific capacity that evolved biologically via natural selection alone? And that's a very different question. And this is the one that essentially is taken to be. And that's what you see in the media and the newspapers and so on, is as if it's inherently biologically endowed. So the analogy here, to give you a sense, is like, let's say we get, it's kind of hard to see a number because it's ubiquitous. We use numbers all the time. It's hard to step back and look at what's going on. Let's take an analogy with, let's say, snowboarding. I don't know how many people here snowboard, but I'm assuming not too many. So we could say, yes, of course, is rooted in biology. You know, snowboarding has a recruitment of, vestibular systems for balance mechanisms, optic flow navigation, limb coordination, and on and on and on. Without any dysfunction over here, you can't snowboard. So you need limb coordination that starts very early on in ontogeny. Now, but in themselves, and this is the point, these limb coordination, optic flow navigation, vestibular system dealing with balance, they're domain general. They're not domain specific. So they're not about snowboarding in this case. They're needed for snowboarding, but they're not about snowboarding. And importantly, they cannot scale up to create snowboarding. It's not like if you really, really have amazing balance and you really improve limb coordination, you really improve optic, then you snowboard. No. You need way more many things. So you have biologically evolved preconditions. Any of these are biologically evolved, like subitizing and large quantity discrimination, but they're not the same as inevitable precursors for what came after. For that, you have discontinuous things like the gap, the symbolic gap I was referring to. So we can't really say that this little baby infant is, engaged in early snowboarding or proto-snowboarding or primitive snowboarding. This is not leading to snowboarding. You can't scale up this to get snowboarding. For that, you need a whole developmental culture for, let's say, having boards to begin with, having thermic insulation. If you do this naked, you die of hypothermia. You need, lifts, because if you have to climb yourself each time, the learning curve is going to be much lower, because maybe at most you do 2 runs a day, not 20 a day, and so on. And all those are cultural developments like writing. So for snowboarding to occur, you need, which are cultural traits. Some cultures have snowboarding, some don't. You need artifacts, biological enculturation that is mediating some of these phenotypical plasticity that would show up in the learning of how to snowboard. So if you now change the snowboarding and I put there something like number, we do have biologically endowed quantical mechanisms like subitizing, large quantity discrimination you observe in many non-human animals. But in themselves, they're not about number. And you cannot scale them up to be number. They just evolve preconditions. But you have to recruit them by certain activities that are now culturally defined. So for number to occur, really you need these cultural traits and preoccupations and artifacts that are largely outside of natural selection proper. So to conclude, the data, when you look at different areas, unambiguously show that humans and other species have biologically endowed abilities for discriminating quantities. No doubt about that. Fish, insects, bees have been studied more in the insects world, different types of vertebrates, mammals, and primates. No doubt. And you don't need, apparently, language, culture, and so on. But the widespread view says, in these areas, in cognitive neuroscience and animal psychology and child psychology, sees directly these abilities as a manifestation of an evolved capacity that is specific for number and arithmetic. The view, then, has problems because by this is meant many different things. We need to tease apart the factors to get something clear, where we can't just equate quantity with number, for the reasons I gave before. We should be much more careful in looking at animal studies. What does it involve for the purpose of evolutionary argument, that is? I mean, you can do all kinds of things with animals and learn amazing stuff. But for the purposes of thinking of what are the evolutionary niches in which the species evolve, then we have to be very careful about what is it that we're doing with them. Also, there's been a lot of downplaying human data. When we really look at this data, we have to modify the theories in a way that we encompass those findings. And unfortunately, with the teleological arguments that are involved over here, it kind of bring into these sort of inaccurate conceptions of biological evolutions. As soon as you see something that you can train in a pigeon or something, an animal, a non-human animal, you would sort of argue that there's some kind of dormant capacity that all you need is to train and boom, you get something like number, for example. So these are inaccurate conceptions of biological evolution. And this, unfortunately, is enabled by this loose terminology, that if we don't get it right in terms of what are we really talking about, it's going to be very confusing to get at these questions. So to move ahead, we must recognize exact quantification is not a biological trait. If we really look at the data, it's a cultural trait supported by symbolic reference, which is not biologically evolvable, was brought forth by cultural practice and preoccupations, if we look at the history of humanity, and along with phenomena that support specific phenotypical plasticity. So that's what I'm kind of talking about, biological enculturation now. And this distinction between quantical and numerical, to disentangle what is really biologically endowed from what is not, and how do you move from one to the next, appears, at least in my perspective, absolutely essential to understand what is exact quantification all about. Now, language may be necessary, as I was saying, but is not a sufficient condition. All languages have natural quantifiers, but by no means they all have exact quantification. So to move ahead, as I said, this is the one I was. To move ahead, we have some questions that are outstanding. What selective pressures may have given rise to quantical cognition? There are some good hypotheses, but we should investigate them. What does it take to move from quantical cognition to numerical cognition? How do these two forms relate to each other? We can't just put all in the same bag. Apparently they're different, and how do they relate, and how do you move from one to the other? What is the role of natural quantifiers in the consolidation of number sense in children? That is a question that almost no one has studied. They studied just the number, the counting, how parents do they count at home, that kind of thing. But the relationship with few, several, many, and so on has not been really explored in this domain. What are the neurological underpinnings of the learning of quantifiers in language, in natural language? Open question. And then building on these biologically endowed quantical cognition, how does exact symbolic quantification get grounded and neurally instantiated? So what would be the actual biologically enculturated neural markers that we could look at in order to understand? And the work of Dan and Sari started in this interesting Nature Review neuroscience paper, looking at the sort of enculturation and aspects of how numerical concepts and numerical ideas get sort of quote represented in the brain. So, although ubiquitous today in the industrialized world, in our lives, numerical cognition, like geometry or music or visual arts or piano playing, should not be taken at face value if we want to look at the big picture of humanity. The answer to the question of what it takes to move from quantical to numerical is not trivial at all. So we can't just put everything in that bag. It's really complicated because, indeed, only some humans, in the right socio-historic context, in the 220,000 years of Homo sapiens history, and after tens of thousands of years, only a few of them have made that leap. And that's us, but only a few of them. So thanks for listening, and I want to thank many of the people who collaborated in various parts of this sort of intellectual path and research. Thank you. That's a good quantifier, yeah, very good. Very useful morpheme there. Good, anyway.
I have like 7 questions, but I'll start with like is a good, and another one. Like
yes, like, exactly.
I'll pick one. I guess, so I was really intrigued by the sort of wheel you put up with placing everything. Is that in your TICS paper?
It is,
cool.
yeah.
I will have to look at that.
I could put it back.
So I wanted to know if you could put, if you could talk about where home signers would fall in relation to that, because, and as well as talk a little bit about enculturated apes. I feel like, and I'm not trying to draw a parallel between those, but I think those are just 2 interesting cases. On the one hand, you know, you have humans who are socially, you know, fully enmeshed, but they lack a linguistic system that is shared with others. I'm just doing this for other people. I assume you have read some of this stuff. So, right, where they have essentially idiosyncratic linguistic systems where they're profoundly deaf, they don't hear the language around them, and so then they're developing their own systems of communication, which no one shares and needs back to them. So someone here is working on exactly how those might be more shared than we thought. But there's some really interesting work on their numerosity. And so I just wanted to know kind of how that fit into the story of enculturation, in particular the relationship of language.
Right.
So at least Alicia Spabin's work on sort of looking at how home signers do in nonverbal tasks that involve, you know, ordering quantities from 1 to 10. They're really bad once you get beyond 4. And once you get out of the subitizing. And her argument, I believe, was that in order to be a cardinal principle knower, you had to be trained with a count list. And so I just wanted to know, like, how that kind of fit into your story.
Well, I would say, yeah, those are interesting questions. But, you know, all those would fall in this kind of the title of this part of the disc, right? You have explicit training, like what you just mentioned, is, okay, here's a way you can do it by counting, and this is how you count. And you may count, you know, by index pointing finger. You may count by moving objects from one side to the next. And you may have different kinds of practices guiding to this important factor that is the exact quantification aspect of it. But you could reach that by many different ways. So, but you need, you're not because you're deaf, you're going to come up with your own system. You know, we don't, I mean, the ideal experiment would be to have, and this is for anyone who studies evolution of language, it's like what is, you know, if you just put a human completely isolated with everyone else, then what happens? But that doesn't happen, right? It's not a non-viable thing. So usually a signer would be part of a community, whether it's other signers or people maybe that communicate at another level. But if they're communicating exact quantification as being super relevant and super important, they would have some tool in which they would lead to that support that discrimination beyond the subitizing range and have names for those things or labels. So it could be that an individual signer may have more of a mnemonic strategy for remembering that maybe 6 is kind of 2 3s or something like that, and therefore maybe that particular idiosyncratic technique may work for certain kinds of things, but you would have to have some kind of scaffolding there. So here, this is just a picture of kind of main categories of how things have been written or signed, but here what I put it was like hand and body signs, because some of them may be signs for, like natural quantifiers perhaps, but not necessarily precise or exact. And some may be for exact and may be compositional, I don't know, depending on the signing. So, but I would say any signer would have to have some kind of symbolic representation or characterization of those quantities. And if that individual is immersed in a group or a microgroup or a society that really cares about those things, it would come up with some kind of distinctions that are going to be robust and pervasive in the use. So
you really would need explicit training in the numeral system. I mean, basically in whatever counting system, because I mean, it's not like you don't use money, because they do use money. So I feel like having culture, the culture.
Right. The use of money tricky because you could have some kind of like you could use money and the work of let's say Sachs and Berkeley, and so you could show that you could have different bills from different colors. And you can know that with this one you can buy a lot of something, and with this one only a few of that something. So you're relying on natural quantifiers codified by a chromatic coding, And of course, what happens with natural quantifiers is that even though there may be one lexical item, the truth is that in practice we have many resources for modifying or adjusting the quantity of those quantifiers. So for example, I could have a prosodic cue to increase the amount. So I could say many, And that change of vowel intensification is just telling you is more than the standard many, the prototypical many. So there's more than that. Or I could use iteration. Many. So I use 4 or 5 times the same lexical item to adjust to, or saying is more than that, and so on. Or you may have adverbial techniques like really many. So now the really is saying is a lot of that. It's not just like many, and so on. So what is interesting is that you have these linguistic techniques that you may say, oh, they only have the word many. But in the ethnography of how that many is used, you can see all this richness for calibrating the need. If you say, oh, this coffee is really, sweet. Well, you only word the word sweet and then really, but you use the really 3 times with prosodic cues saying it's much more sweet than what you expected and so on. All those without exact quantification. So I would imagine, and this is open research, in these signers, for example, you may have modifiers of all those kinds of things to adjust quantities in ways that is not just you have a sign for many or a sign for few, but you also see what are the modifiers calibrating, adjusting the quantity for the needs of the particular setting in which they are. But whatever they are, they would have to be socially conventionalized. So if I want to modify my many by saying many, it's like, is that nothing? Or, has to be a specific type of prosodic cues that is conventionalized, may not even be in the grammar when you write the grammars of this Aboriginal language, and so you rarely pay attention to those things. Now people are starting to be much more subtle. But usually is dictionaries, lexical item, grammar in the classic sense, but these practices are not really observed much, unfortunately. Yeah, and then. Yeah.
So I really appreciate the sort of the rigorous thinking throughout and the attention to clear terminological and conceptual distinctions. That said, I want to turn that lens around a little bit and push you a little bit on one of your concluding statements, which was that number is not biologically evolvable. And it seems to me that you're combining 2 arguments in there. One is that empirically it did not biologically evolve. So the Australian Aboriginal language says, look, we had a long period of time, lots of linguistic speciation, and yet we don't get this happening. And then the symbolic reference gap argument is it couldn't biologically evolve. right? And that single statement, not biologically evolved rule, smuggles in the empirical claim and the theoretical claim. It seems to me the empirical claim is quite strong. The theoretical claim is a little more tenuous because there are animal systems of communication that seem to have some symbolic capacities, whether it's verbal alarm calls or prairie dogs or whatever, right? So, in principle, it isn't impossible that you could get number evolving with reliance on symbolic reference. But that then leads to the question of, if we take the empirical claim as accurate, which I think it is, why didn't it evolve?
Right.
And there, your sort of, recent cultural history story, I think, is quite reasonable. But we could also ask the converse, which is, what would be the adaptive advantage of having numerical rather than quantical capabilities in other species?
Right.
That is, when are there significant adaptive challenges such that a quantical approach is insufficient and a numerical approach is superior? And it seems to me that they're very, very rare. That in general, if you're looking at, time allocation, return on investment in foraging, whatever it is, that quantical suffices. And in fact, you can have that not only with regard to, say, visual assessments, you can have it with regard to, endogenous cues of, caloric intake and so on, right? And the only example that I can think of where there is any selective pressure in a non-human species for some numerical ability is in host species to nest parasites like cuckoos, where there's an evolutionary arms race where they can, they can match the appearance of the egg, and there is a selective advantage in being able to count the eggs and know whether you've been parasitized, right? That's a small number, right? So those clutches, I'm not the zoologist, I don't know, but I don't think they're more than 5, right? And it's a very, very specialized, narrow domain. So I think you can make the claim numerical abilities didn't evolve biologically, they only evolved culturally on the basis of a biological substrate. And you can make the claim that that's not an accident because there isn't selective pressure outside of particular cultural contexts for this capability. But that's not the same as saying they couldn't evolve.
Yeah, I think you're right. I think when I take this quote from Terry, is that the actual specific symbolic form, let's say the English language as such, that cannot be biologically evolved. You may have other, so I think you're absolutely right that you have to have selective pressures. And the question is, what would be those selective pressures? Maybe we could find here and there like very rare cases, and it would be probably in a small range, and usually it would be without necessarily a categorical response, which is one criterion I'm adding here to the number. So it would be like a, percentage of responses or ratios of things like that, which would satisfy that behavior and the conditions. But I agree with you that if we look at, for example, classic Weber-Fechner's law for perception and so on, yeah, there is probably a non-linear aspect of perception in the compression of how you distinguish, that it doesn't make much of a difference, to put it boldly, but something like whether you see 26 lions or 27 lions running after you, because it doesn't make a difference. If you see 1 or 2, then it does. And so on. So it looks like anywhere you look in the perceptual system, loudness and brightness and so on, you have that particular compression, which would lead also for numerousness. It's easier to discriminate when the stimulus intensity is low than when it's high. So it looks like there is a threshold of when really the exactness and effortlessness of the response has a payoff. And I think some of the arguments have been used for other people say, why do we only have, how do you call this part in the knuckle? Yeah. Why don't we have 7 or 8, to grab really fine things, And then, yeah, but we only have, let's say, 1, 2, 3, and that's it. And then some people say, well, because beyond that, you just have this very interesting part of the anatomy, which is kind of soft and always moist. So that by then, it's like anything that is tiny and light, you can grab it that way without counting anymore on it having another piece of anatomy that has all kinds of costs and so on. So it could be that here's the same thing. You have one mechanism, which is this kind of the subitizing range, and then after that is more like you discriminate huge amounts. Those may have had a good like a good quote solution for selective pressures, for example. But I think you're right in the sense that they could evolve something symbolically. Maybe it could exist. The question is, what would be really to push it well beyond the subitizing range? Is an open empirical question, but I think here the claim is more than the specificities of the symbolic pattern. So it would be like the English language, let's say, or some language with a certain type of deictic system, with a certain type of phonology, and then those kinds of things may not be biologically evolved because you need to learn it in ontogeny. I think that's more like the claim, not like the that you could not, in principle, have some kind of symbolic reference per se, so to speak. And that kind of links a little bit to what you asked earlier about enculturated apes and so on. Yeah, you could sort of create niches of human, non-human primate interaction where you cannot create one of those things. And in fact, you have that with your domestic dog at home, when you have certain patterns of certain kinds of things where you create mini conventions, and things stand for other things and so on. So, in that sense, I don't think the gap is of this nature. I agree. Yeah, you're right. Thanks for your comment. Yeah, please.
First, thanks for a super interesting talk. I wanted to ask a little. I was interested in sort of the distinction between preconditions and precursors, and I was thinking a little bit about some of the characteristics of numbers that you had described. And so I guess what I'm wondering is, to what extent, if any, does the actual ability to make quantitative distinctions perceptually actually bear on the numerical capacity? So is there any evidence that people who are either, by virtue of an acquired or inherited sort of dysfunction in quantitative distinction, are they still able to sort of learn and employ and understand numbers, or is that sort of like an integral causal component in the numerical ability?
You mean an individual who has like enhanced capacities for discriminating?
No, so if they have say had a stroke or something and
Yeah.
a region of the brain that inhibits the ability to make like quantical distinctions,
Yeah.
does that also does that have a causal effect on their numerical ability as well?
I see. Well, I mean, there is research showing in neuropsychology that when you have, let's say, severe injuries in the intraparietal sulcus, then usually occur at a certain point in age when you're already adult, and then some aspects of quote number crunching are affected by that. So it seems to be that, for example, lesions in the IPS would lead to dysfunction of that sort. Now, the question is, well, but what is the IPS for number crunching, evolutionary speaking, or is it that the IPS is a great neural tissue to be recruited to support things like numerical distinctions and that kind of thing? Sorry, go ahead.
Well, I guess I'm just thinking about some of the like prototypical characteristics of numbers that
Yeah.
you described, which it seemed like a lot of those elements were sort of independent of what actually matters for quantical distinctions.
Mhm.
So I'm wondering to what extent the evidence suggests that this is actually sort of a precondition for numerical ability, as opposed to just being sort of two separate tasks that happen to bear on the same domain but are not actually like meaningfully causally.
So the this, what is the this?
You get dissociations is what he's asking. So somebody can be very good at quantical distinctions and very bad at the numerical, or the reverse.
Right.
What happens when you knock one of those out?
Right.
So if the quantical is a precursor for the numerical, what happens if you knock
Yeah, well, thanks for clarifying. um, I would say that that question is a very interesting theoretical question. I don't think in practice you can observe it really, because quantical would mean something like you have no exposure to any symbols whatsoever. And because we have many ways for doing symbolic reference to number, morphologically, symbolic, acoustically, in different notation types and so on, different graphings and so on, I would have trouble to see when do you really knock out the symbolic aspect and you just stay with this enhanced quantical, let's say. And also, as soon as you are in this business of human practices, you get sometimes subitizable things that get to be symbolic. Let's say, if you see the picture or an icon of the side of the die with 3 dots in diagonal, well, though you are subitizing them, you may not be counting that there's 3, but at the same time it's a symbol for 3. In certain, or 5 could be maybe like 2 here and then 1 in the middle. So it's almost subitizing range, or certainly it is 4 like that, but it becomes as a symbol. And in fact, a lot of if you look at the history of numerals, a lot of the numerals between 1, 2, and 3 in many written languages stand with some kind of subitizable pattern of dots and bars. In Japanese or Chinese is a number of bars that extensionally coincide with the subitizable experience. So I would say in the case of human, this question, which is really interesting, I think is very hard to disentangle, because humans are cultural beings from day one or even before, because of how your mom eats and what sounds she produces when she speaks and so on, and you're just inside the belly, So that's kind of very hard to disentangle purely, but I would imagine, this is now a conjecture, but I would imagine that because the symbolic aspect is so rich with so different modalities, that you may have maybe, for example, some visual patterns disturbed, but maybe you could recruit acoustic one, which are maybe poorer, but still you can rely on those, and so you could sort of limp your way around by not being purely quantical, so to speak. But open question, but yeah, interesting theoretical question. Yes, please.
If there is consensus as to which model will be the quote true model,
Okay.
what would be the consequence of that? Or what other boundary would that lead to that had to be explored?
Oh, thank you. Yeah, well, I think the consequence is more like first, how do we do science? Second, what are the implications for societies of the science we do? For example, there's a lot of work done with a more nativist form, training, precisely going to the previous question, training the discriminatory capacity early before you get into, quote, symbolic, as that is going to enhance the mathematical capacities, because they seem to correlate with tests that you do later in middle school and that kind of thing. There's a lot of, it sells well, at least in the West and in the industrialized society, that you could do things early in life. If you could start having your toddler walking earlier, it's going to be better, because it walks 2 months earlier than other, is going to be having advantage and so on. Now we know there are all kinds of issues with spine deformation and scoliosis that are related to efforts of parents done a few decades ago of trying to stand the kid and trying to walk the kid and so on, when the spine is not ready, all the muscles are not ready to support the weight of the forming spine and so on. So I think this sort of overlooking at, which is well received in the West and in the industrialized world, that things can be found in nature at the level of the genes, that in general is well received. And things that are more cultural, or how the complexity is kind of like a boring explanation, or like, we want to find the gene, we want to have the localization, the IPS and the occipital lobe, the particular chromosome, and those are well received. So a view that goes in that direction tends to say, okay, if that's the case, then you want to have kids that have the right genes, or the right, from the very early on, the right, stimulation of the visual system and that kind of thing. When in fact, if we look at this other side, it's more like, well, no, it depends on many other things that don't necessarily rely on directly and so on. So I think it's the type of education you think of, the type of curriculum, the type of citizen you want to have in society, of having a good sense of numeracy, which has many more of these other properties of number than just perceptual and so on. So I think it has social implications in how we conduct and we conceive education, which these days, I would say a lot of projects funded by NSF and NIH, for example, are based on improving the ANS system by simulation and that kind of thing. So, which I don't know whether it has a good implications, other kinds of things, or that you could improve math lessons by doing these kinds of things, as opposed to improving the teacher quality, the teaching of the quality, of the teachers and how they are prepared and how. I think those are implications, I think, from this side of. Thank you. You're welcome.
So,
yes.
Unfortunately, we are out of time
okay.
right now, but please come. You can save your questions later. So if you could just join me in thanking our speaker again.